We've already seen the geometry. How do we describe basic geometry using the basic elements, like a point and a vector? Now we look at how do you represent uh, how do you represent both points and vectors in graphic systems. So this coordinate systems were representing. Okay. Now let's look at first regarding what is a reference system. We need a frame of reference to points and objects to relate to the physical world. Uh, so where there's a point, if we want to look at something like an object, we need a reference point, right? So for that, we need world coordinates and camera coordinates. So the general coordinate system, which we have, is normally it consists of a basis. The vector space which we are trying to represent, it has basis, and any vector in that particular space can be represented using a linear combination of these basis vectors, right? So how do you represent a vector or is normally represented by it's a set of all the coefficients while we're taking linear coefficients. For example, if v is equal to alpha 1, v1, alpha 2, v2, etc., alpha and vn, then the list of scalars, alpha 1, alpha 2, etc., alpha n, is a representation of the vector with respect to the given basis. So you normally represent this as a column array. We assume that the basis is fixed or it's already known. Uh, but the issue with this is vectors, they don't have a fixed location. They can be at any point in space. So vector, they don't have a fixed location. But in order to have a fixed location, we need to also specify an origin. So whenever we are specifying an origin along with the coordinate system, it's called a frame. So you add a single point to the basis, like the origin, and it forms an affine space. So what is an affine space is this space where all the transformations on this points, linear relationships between these points are actually preserved. We'll look at this in detail later. So let's look at the representation of frame. So a frame is represented by not just a coordinate system. We need a point P0 along with the basis vectors. So within this frame, every vector can be written as v is equal to alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. And every point can be written as p is equal to p0 plus p0 is actually the reference point plus beta 1 plus alpha 1 v1 plus beta 2 v2 plus beta 3 v3. But there is some issue which we have to deal with. Suppose we already seen how we represent vectors in a particular frame or a coordinate system. We just use any vector can be expressed as a linear combination of the basis vectors. Then we'll represent them as using the coefficients which form the linear combination. So for a point, we have P0 plus beta 1, V1 plus beta 2, V2, etc., beta and Vn. In the 3D case, we have beta 1, beta 2, and beta 3. That's how we represent a point. And a vector we are representing as alpha 1, alpha 2, alpha 3. So there is an ambiguity between when we're given a column vector like this or a row vector, whatever, convenient. We are not able to figure out whether it's a point or a vector. Right? So in order to fix this, we also add another additional component to this representations. So to actually do this, we have to first define two operations, 0.p, where p is a point and 0 is a scalar. P is actually 0 and 1.p is p. So any vector which is represented as alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, instead of just alpha 1 alpha 2 and alpha 3, we represent them as alpha 1 alpha 2 alpha 3 and 0. And the basis, the corresponding basis, instead of representing v1 v2 v3, we also add the point p0 to it. So this is how we represent alpha 1 alpha 2 alpha 3 along with the 0. And if it's a point, we represent them as beta 1 beta 2 beta 3 and 1. So such a representation is a 4D representation of the coordinates, and such a representation is called the homogeneous coordinate system. So basically, the homogeneous coordinate system of a 3D point x, y, z is given by x dash, y dash, c dash, and w. Along with the first 3 dimensions, you also have a fourth dimension, which is a non-zero thing. If it's a vector, you don't have a fourth. The fourth component will be 0. And normally, the fourth dimension, fourth component is actually 1. If it's not 1, then you have to divide each component by w to make it 1. Also, if you're given a homogeneous coordinate of a 3D point, then suppose the fourth component is not 1, then the way to obtain back the 3D point is by dividing x, y, and z with the last coordinate w. What is the basic advantage of using homogeneous coordinate system in computer graphics? So the main advantage is all the underlying representations of points and vectors in computer graphics. We can use a standard implementation. So all the transformations which we're doing on these points are normally represented as 4x4 matrices, which includes rotation, translation, and scaling, and also shear. All these transformations which we do on points are basically a 4x4 matrices, and so we can easily multiply this 4x4 matrix with a 4x1 coordinate system. So you can just need to optimize the graphics hardware pipeline for this 4D representations. You don't have to specifically design something for point and vectors separately. Let's end this discussion here.